All right. Hello, everyone. I'm Ms. Turk, back with some tips on the 4.5.3 test. All right. Question 1, Part A, look at 4.1.1, page 4. For Part B, look at 4.1.1, page 5. Part C is worded really weird. Change it to what is molar mass? The molar mass of a molecule makes no sense. What is molar mass? What unit is it in? Okay. So it's the number of grams in 1 mole of a substance. Okay, and the units are grams per mole. All right, it's the number of grams in 1 mole of a substance, or the mass of a mole of a substance. Question 2. Okay, so what is the molar mass of NaCl? So like you saw in your reading, the molar mass, what we normally think of as the atomic mass, can also be thought of as the molar mass, okay? So these numbers down here are the atomic mass of the elements. It's the number of AMU in one atom, okay? So for lithium, it's 6.94 AMU per atom. AMU is just a really small unit of mass. But if we scale AMU up to gram, there's 6.02 times 10 to the 23rd AMU to make up a gram. And grams are much more useful to us in the lab because our scales measure in grams, not in AMU, okay? So there's 6.02 times 10 to the 23rd AMU in a gram. So if we scale AMU up to gram by that amount, and then we also scale the number of atoms from AMU per atom to grams per mole of atoms. So we also scale up the number of atoms by 6.02 times 10 to the 23rd. Both of those things, so let me back up here. So lithium is 6.94 AMU per atom, okay? But if we scale the AMU up to grams, because grams is more useful in the lab, and we scale the atoms, instead of just talking about individual atoms, we're going to scale it up to moles of atoms, okay? So that means we're scaling atoms up by a factor of 6.02 times 10 to the 23rd, and we're scaling AMU up by a factor of 6.02 times 10 to the 23rd, because that's how many AMU. AMU is very small. That's how many AMU it takes to make 1 gram. So since we're scaling up the numerator and denominator by the same amount, the 6.94 is going to stay the same. So what we normally think of as the atomic mass, the AMU per atom, is also the grams in a mole of atoms. And this is more useful in the lab because a gram, our scale measures in grams. A mole of lithium is enough that we can see it and work with it, whereas 1 atom of lithium, we can't see it, we can't weigh it out, it's too small. So that's why we kind of batch atoms into moles, because it's enough that we can see and we can measure the mass in grams. So when they ask for the molar mass of NaCl, you need to add up the molar mass of Na plus the molar mass of Cl. So do 22.99 plus 35.45. And again, the units are grams per mole, okay? What is the maximum number of moles of NaCl an adult should consume in 1 day? Well, it says up here, you should eat no more than 6 grams of salt. Salt is NaCl. So salt is not just sodium, it's sodium chloride. It's sodium bonded to chlorine. It's not sodium by itself. A lot of people have that misconception. So 6 grams of NaCl is the maximum. Okay, so I want you to put that over 1. We're going to do a conversion, dimensional analysis conversion. We want grams to cancel, so throw grams of NaCl under the bus. Okay, and then it's asking for the maximum number of moles, okay? So the units we want to get to, we put on the top, okay? So I want you to look up here at whatever grams per mole you wrote down, okay? So whatever your answer was to A, that was the grams in 1 mole. When we say grams per mole, that means it's the grams in 1 mole, okay? So whatever you have here goes with grams, and that's the equivalent of 1 mole. So wherever moles ends up in your conversion, that's where you put the 1. Okay, and then whatever the molar mass is goes where grams is. Sometimes grams is going to be on the top, sometimes grams will be on the bottom. Wherever grams is, that's where you put the molar mass, and keep in mind that's the grams for every 1 mole. So the top and bottom are equivalent, okay? There's whatever grams for every 1 mole of NaCl. For every 1 mole of NaCl, there's whatever you got for the grams, okay? And then once you have something written there, I'm just going to call it X. You can cancel out grams of NaCl because it's on the top and bottom. And then you need to multiply straight across the top. 6 times 1 mole of NaCl is 6 moles NaCl. Then multiply straight across the bottom, 1 times that whatever you wrote here, and write that down. And then you do top divided by bottom, and that'll be the moles of NaCl. C was also worded very strange. I don't know who wrote these questions. What is the maximum number of formula units of NaCl in 1 mole? That doesn't make any sense. What is the number of formula units of NaCl in 1 mole? So we have 1 mole of NaCl, okay? And then we're going to throw moles NaCl into the bus, and we want to know the number of formula units, okay? So you might be wondering, what is a formula unit? A formula unit is like it's essentially the same thing as a molecule, but for an ionic compound. So for a covalent compound like water or carbon dioxide, it's made of molecules. So if we have a mole of water, we have 6.02 times 10 to the 23rd molecules of water. But if it's an ionic compound, we don't call it molecules, we call it formula units. So if we have a mole of NaCl, we have 6.02 times 10 to the 23rd formula units in 1 mole. Okay, so you can cancel moles. Just multiply 1 times that is that. And you probably knew that answer without even writing it out, because, you know how many things are in a mole, okay? There's always 6.02 times 10 to the 23rd things in a mole. If that thing is an ionic compound, it's formula units in a mole. If that thing is a covalent compound, it's the molecules in a mole. If it's an element, not a compound, it's atoms. Like something like lithium or carbon is made of atoms, because it's not a compound, it's an element. So think of this Avogadro's number as the number of things in a mole, whatever the thing is that you're counting. In this case, it's formula units. All right, for part D, a certain brand of canned soup contains 2.26 grams NaCl in 1 serving. What is the molarity of NaCl? The formula for molarity is moles per liter. Okay, so we need to set up a conversion so that we end up with moles on top and liters on the bottom. Okay, so canned soup contains 2.26 grams NaCl in a single cup serving, so per 1 cup. Okay, so the top and bottom are equivalent. 2.26 grams NaCl for every 1 cup. Okay, and then we need to convert that to moles per liter. So we're going to focus on getting the top converted into moles, and then we'll deal with the bottom. So let's let the cup sit there for now. Make this grams NaCl, and we want to convert to moles. So you just do you use the same conversion factor you had here, okay? So figure out use the molar mass, the grams in 1 mole here. Then you can cancel that. Now we have moles on the top, which is good. So we're going to let that stay. Now we're going to focus on getting cups to cancel. Because cups is in the denominator, we need to put it in the numerator, okay? And we want liters to end up on the bottom. We want moles per liter to be the unit of our answer. If you look right here, I don't expect you to know how many cups are in a liter or whatever, but this is the relationship. For every 4 cups, that's the equivalent of 0.946 liters, okay? So they'll always give you information that you need to set this up, okay? So remember, the top and bottom need to be equivalent. 4 cups is equivalent to 0.946 liters. So be sure you get your units written down first. I knew I needed cups on the top and liters on the bottom. Then fill in the numbers to make the top and bottom equivalent. So you can cancel cups. And now we're in moles on top, liters on bottom, which is what we want. Okay, so you just multiply straight across the top, 2.26 times 1 mole times 4, write your answer down. Then multiply straight across the bottom, 1 times whatever you have here times 0.946, write that on the bottom. And then you do top divided by bottom. Don't leave it as a fraction. Do top divided by bottom to simplify it. And then the units are moles per liter. Or you could write a capital M, that also means molarity. Either of those is fine. All right, when table salt is added to water, the ionic compound dissolves. Does this represent a physical change or a chemical change? How can you tell? So this one, it would be a physical, dissolving is obviously a physical change. Okay, that's because the substances stay the same. The salt still tastes salty. The water still watery. No new substances were formed. All right, scientific notation. Okay, so to do scientific notation properly, you need to move the decimal until you get a number between 1 and 10, okay? So obviously this number is not between 1 and 10, but if I move the decimal this way and I make it 1.06, that is between 1 and 10, okay? And then you do times 10 to the however many times you moved it. We only moved it once, okay? And if the original number was less than 1, you make the exponent negative. If the original number was small, it's going to have a negative exponent. If the original number was big, it's going to have a positive exponent. So, and you can type it in your calculator to double check your answer. Just type 1.06 times 10 to the negative 1, and you get 0.106, which is what you started with. Okay. All right, negative 178. That is not between 1 and 10, okay? Right now the decimal is here, we just don't write it. So you need to move the decimal till you get a number between 1 and 10. Is 17.8 between 1 and 10? No. Is 1.78 between 1 and 10? Yes. And don't forget this is negative. Negative 1.78, okay? Times 10 to the, and we moved it twice. And it's going to be a positive exponent, okay, because this was a number greater than 1. So a big number, even though it's negative, I shouldn't say that. It's not, the absolute value is bigger than 1. I know it's a negative number, but it's not like a decimal number like it was in part 1, okay? And you can always double check your answer, negative 1.78 times 10 to the second, and you get negative 178. So you can always check. And then these ones, you're going to go the other way. So if there's a positive exponent, you're going to end up with a big number, okay? So move the decimal 6 times in a direction that gives you a big number, and any spots that don't have a number, fill it in with zeros, okay? Whereas this one has a negative exponent, so you're going to get a small number. So move that decimal 4 times to get a smaller number, and then fill in the empty spots with zeros. And you can also just type it in your calculator to get the answer. All right, percent composition by mass. Percent composition is part divided by whole times 100. So you always need to do part over whole times 100. So, and it's percent composition by mass, okay? So look at the mass of lithium. So we have LIBR. That's the whole thing, is LIBR. So it's asking for the percent that's lithium. Okay, so just the lithium is 6.94. And then the mass of the whole thing, you would do the lithium, 6.94, plus the bromine, which is 79.9. And you get 86.84. That's the mass of the whole thing. And then you do times 100. So 6.94 divided by 86.84, you get 0.0799. And then to convert that to a percent, like I said, you need to multiply by 100. And you get 7.99%. Okay. Now we want the percent that's bromine. Okay. So that's the other one. So you would do the bromine, 79.9, divided by the mass of the whole thing, which is still the same. The denominator is going to be the same, multiply by 100. All right. Now we're going to calculate the empirical formula of a molecule with the following percent compositions. Use the table to help with the calculations. I don't necessarily find this table super helpful, but we'll use it. Okay. So let's say you have a compound, and you know by mass, it's 55% gallium, 45% fluorine, okay, by mass. And we want to figure out what's the formula of this compound. Is it like GAF? Is it GAF2? Is it GAF3? Is it GA3F2? Is it GA4F1? We've got to figure out the ratio of galliums to fluorines. We know the mass ratio. We know by mass there's a little bit more gallium than fluorine. The problem is gallium and fluorine atoms have different masses, right? So we got to account for the fact that the numerical ratio is not the same as the mass ratio, okay? So whenever you're dealing with percents, it's always easy to just assume you have 100 grams of stuff. So we got 100 grams of stuff, whatever this compound is, gallium fluoride. We just don't know the formula for this compound. So if we had 100 grams of stuff and it was 55% gallium, that means we have 55 grams of gallium. And if it's 45% fluorine by mass, we have 45 grams of fluorine, okay? The problem is that's a mass information, whereas we need numerical information. And remember, moles are a unit, a numerical unit, okay? Moles tells us how many, whereas grams tells us how heavy. So what we're going to do is convert 55 grams of gallium into moles of gallium. And then we're going to convert 45 grams of fluorine into moles of fluorine. Like that. Okay. So the relationship between grams and moles, the grams per mole, is the molar mass. So look on the periodic table. Okay, and for gallium, the molar mass is 69.7. And remember, the molar mass is not the moles in 1 gram, it's the grams in 1 mole. Hold on, I'm using the wrong periodic table. Yours might be a little different. 69.72. Sorry, 69.72. So remember, this is the grams in 1 mole, not the moles in 1 gram. It's the grams, put it on the bottom of grams, in 1 mole. And then fluorine is 19.00 grams in 1 mole. Okay, I'm going to switch colors here. So, grams of gallium can cancel. Multiply straight across the top, you get 55 moles of gallium. Straight across the bottom, 1 times 69.72 is 69.72. Then multiply across the top, 45 times 1 mole of fluorine is 45 moles of fluorine. And then 1 times 19 is 19. So do 55 divided by 69.72, and you get 0.78887. Keep extra digits in your answer, okay? And that's the moles of gallium. Then we're going to do the next one, 45 divided by 19. You get 2.368. All right, so we got to kind of tease out a ratio, okay? I'm not good enough in mental math to tell what the ratio is. I can't tell by looking how many times bigger this is than this, because I can tell we have more fluorine atoms, okay? We have this many moles of fluorine, but only that many moles of gallium. So I know we have more fluorine atoms than gallium atoms. I just need help figuring out how many times bigger this is than this. I'm not good enough in mental math to tell. So when you can't quite tell how many times bigger one thing is than another thing, divide them both by the smaller number. Okay, so this gives me a 1, okay? And this, I'm going to divide by 0.78887. Look at that. It gives me 3.002. It's essentially 3, okay? So you can round that to 3. It's a 1-to-3 ratio, okay? That's the mole ratio. That's the numerical ratio, not the mass ratio. Mass-wise, we had more gallium than fluorine. But the thing is, each gallium atom is heavier than each fluorine atom by a lot. So even though we had more gallium than fluorine by mass, numerically, we have 3 times more fluorine atoms than gallium atoms. It works out to a perfect 1-to-3 ratio, okay? So what that means is the empirical formula is the lowest whole number ratio. So the 1 goes after the gallium and the 3 goes after the fluorine. So it's going to be GA1F3, or most people just say GAF3. Okay, GAF3. That's the lowest whole number ratio. I know it's a 1-to-3 ratio. The thing is, the actual formula might be bigger than that. It might be GA2F6, a 2-to-6, or it might be, I don't know, GA10F30. But I don't know what the actual formula is, but I know the empirical formula, the ratio is 1-to-3. Okay. So for part C, determine the molecular formula of a molecule having an empirical formula of NH2 and a molar mass of 32 grams per mole. So this is kind of what I'm talking about. So for this compound, we know the empirical formula. This is the lowest ratio. This one's going to have a 1-to-2 ratio, just like this one had a 1-to-3 ratio. Okay. It's NH2. But in reality, it might be, if that's the lowest ratio, it might be N2H4, or it might be N3H6, or it might be, I don't know, N5H10. It could be any of those things. We just know that the ratio, the lowest whole number ratio is 1-to-2, okay? So what we need to do is to figure out we know that the molar mass is going to be 32. So let's figure out the molar mass of this. So we have nitrogen, which is 14.01. And then we have 2 hydrogens, and each of those are 1.008. So I'm going to do plus 1.008 times 2, because there's 2 hydrogens. And you get 16.026. And I can tell that if I multiply this by 2, I'll get that molar mass, okay? So I just need to scale this up by 2. So instead of N1H2, I'm going to scale it up to N2H4. And let's just double check that that's going to have that molar mass. So you have 14.01 times 2 plus 1.008 times 4. You get 32.052. Which is, it's the same. Okay, so that's how you can tell it's N2H4. All right. For this next part, it's predicting products. Okay, so first we need to use the activity series to figure out if this reaction is going to happen. If you look on your activity series, I don't have it right here. Oh, it's not on here. Okay, but if you were to pull it up, you would see magnesium is near the top. Magnesium's more reactive than zinc. So magnesium would rather be in a bond compared to zinc. Magnesium's more reactive. So if they switch spots, they're going to get what they want. Okay, so these are going to switch spots because it's single replacement. So just write down what the formulas would be. Notice zinc has a charge of 2+, so when magnesium becomes an ion, it will also have a charge of 2+. That's what they're telling you right there. Okay, so just write what the products would be once those two metals have switched spots. Explain your answer, you don't have to do that. And what kind of reaction is this? You can go back and look at the reaction types. Okay. For part B, magnesium sulfate is added to sodium hydroxide. Balance this equation. Okay, so I'm going to put spots in the front of each one so you can balance the equation, because you'll see like right here there's only one Na, but this side has two Nas, so you'll need to put something in front of the NaOH to make it balance. And then once it's balanced, then you're going to use the solubility table to predict if a precipitate will form. So the solubility table's right here. It's on the back of the sheet I emailed to you. It's also somewhere in the textbook. So we need to figure out if there's a precipitate. A precipitate is something that is insoluble, okay? A precipitate is insoluble. So if, based on the chart, one of these products is insoluble, a precipitate will form and a reaction will happen. However, if both of these products are soluble, there won't be a reaction because you won't see a precipitate. Everything will just stay dissolved in water, okay? So for part 3, I'll let you figure out the type of reaction. It's either synthesis, decomposition, single replacement, double replacement, or combustion. And then for part 4, rewrite the balanced chemical equation adding state symbols for all compounds. Okay, so what you need to do, what I'll tell you is that these two things are dissolved in water. So write AQ after both reactants. And then once you've looked at the solubility table, you should be able to tell if both of these dissolve in water, you would write AQ after them. But if one of them is if it's soluble, write AQ after it. If it's insoluble, you write S after it because it doesn't dissolve in water. That's your precipitate. All right, and then for part C, the iron 2 chloride, you can omit that whole thing. Omit 1, 2, and 3. You don't have to do any of that. Okay, and then for part D, C2H4 reacts with oxygen, heat is given off. So whenever you have something reacting with oxygen, it's going to be combustion. And combustion of a hydrocarbon always leads to CO2 and H2O every time. Okay, so the type of reaction is combustion. All right. I don't think you have to balance it. It doesn't say you have to balance it. So those are the answers to part D. And then a structural formula for question 6. You're going to have to draw this on your own paper and then insert the drawing. Okay, I'm going to draw the structural formula for something else. I'm going to draw for C3H8 because I don't want to give you the answer to this. The structural formula just shows all the carbons. Okay, for hydrocarbons, like these carbons are all going to be stuck together in a chain. And then any side that doesn't already have a bond is going to have a bond to hydrogen. Like that. So if it was C3H8, that's what it would look like. Whoops, that's just one line. I'll let you draw it for C6H14. And then the stick or skeletal drawing is super minimalistic, okay? Organic chemists who are chemists who deal with hydrocarbons get really lazy. They get so sick of drawing all the carbons and hydrogens. So basically, they just draw a line to represent the bond between from this carbon to this carbon, and then they draw another line to represent the bond from this carbon to this carbon. So it's essentially just like, that's all they would draw, okay? These bond angles, I know they look like they're in a straight line, but they're not. So that's why there's a little bend every time. And then if there was a fourth carbon, it would be like that. If there was a fifth carbon, it would be like that, you know, so you can kind of take it from there. So each of these points is a carbon, and that's just implied. Any organic chemist that looks at that knows there's a carbon at every point. And then each carbon, if there's on all the sides that don't have a bond to another carbon, you need to envision bonds to hydrogen. They don't draw it. So everyone that sees that knows, okay, well that's, you know, each of those is a carbon. And then any of the sides that don't have a line, they know to visually in their mind insert bonds to hydrogen. Same thing with, like, you probably have seen, you know, things like this drawn to represent molecules and stuff like that. When you see molecules that are hexagons, each corner of the hexagon is a carbon. And then each carbon is bonded to two other carbons as well as two hydrogens that they don't even bother to draw. So when you see like fancy looking things like that, and then maybe they have like a bond to something else, you know, that's what they mean. All of those, every intersection or every kind of point where something is a carbon. All right, so hopefully that helps with what was the name of this test? 4.5.3 test.